Thank you, David, for the nice introduction. So, as he already mentioned to you, like the idea of my talk is to not say that AI is an evil that's going to destroy the world or gonna take away our jobs and these kind of things. Of course, maybe those are relevant topics, but today I'm going to talk of more realistic scenarios, more realistic safety issues that we already have in AI. I hope you can hear me now. The issues that we are already facing, which is how do you even begin designing a safe AI model? How do you even begin using AI technology in a safe and reliable manner? So I'm going to give a foundation of this safety development of AI, and I'm going to talk to you about the inherent fragility we have in our machine learning algorithms. And these are the algorithms that still are running most of your AI systems. When someone tells you he has an awesome artificial intelligent large language model, all it means that he has a machine learning algorithm run on a very big amount of data, training a mathematical model. Okay, these are nothing more than stochastic parrots. So and that's why the route towards safety should start from the root of developing these models, and hence machine learning algorithms. And so first I'm going to introduce why these machine learning algorithms are inherently fragile, why they can be not relied upon, why they can compromise the safety of AI models. And then optimistically, I'm going to provide you some steps that we are at EPFL taking towards ensuring these machine learning algorithms are robust to some of the corruptions in the data or corruption in the computing that go or are probable during the training procedures. Okay. First, let us all agree that we are all impressed by AIs these days, okay? And there's a reason for that. There's a reason these AI models have been defeating one of our greatest champions in games like that were thought to be the epitome of human intelligence, okay? No longer the case. AI is becoming more and more human. It's exhibiting more human-like behaviors. And I'm pretty sure if you query ChatGPT, she will be happy to share much more of these achievements of AI in recent years. But we are not interested, at least many of us are not just interested in these games, okay? We want to get serious about AI. Now, what does that mean? We want to use AI in systems that are going to help us, that are going to improve our everyday services. For example, healthcare. It's been said that because the rise in the complexity and the availability of data in healthcare is getting more and more difficult for manual processing of this data. We would like to use these AI models, these machine learning algorithms, to process these data in a beneficial way. Similarly, people are using AI these days on autonomous driving. People have started using them in military to design strategies. In finance, when you apply for a credit card today, your profile is being scanned through an AI model, and that decides whether you get a loan or a credit card or not, okay? And this is no longer just a gimmick. It's no longer something like, it's no longer, let's say, a circus clown. It's something that's going to affect my daily life. It's a matter of life and death in many cases. So now it's obvious for us to ask whether these models, these algorithms can be trusted. Now, to define what I even mean by safety of machine learning models, let me give you a very quick overview of how these machine learning models work. You start with a model architecture, which is nothing but a structured array of some multiplication and additive operations. You take this model and you take some data from which you want to extract some information. For example, if you are training a model to identify cats in images, you will take a lot of images from the internet, often, of cats, and then you would query this data with your model. You query this data using the model through a machine. And you do this over and over again, hoping that eventually this model is going to do what you intend. Recently, what the industry and many of us has in computer science and machine learning have discovered is that the more data you feed the better the accuracy gets. However, to harness this information, the complexity of rising volume of data, you need more parameters. You need larger models. And that's why today you see why we are just modeling models with trillions of parameters over trillions terabytes of data. So the simple formula we have at our hand, which is driving the modern AI technology these days, is more data, use large models, and you get better accuracy. Okay, it's a very simple formula, very easy to do. We have a lot of computation power these days, Google, Meta, Amazon, and I don't even know how much computation power they have, but apparently we don't need supercomputers, that's for sure. They have enough data centers to handle whatever computational needs you may have. For example, this is already, if you guys are following the trend of GPTs and chat GPTs, this is already a very obsolete number. This was 3 years ago. And what's going on right now is every year we are coming up with a model which is 10 times bigger than the model last year. Same with the data. And of course, with all this power, you need to have a lot more computational responsibility to handle, to harness this rise in the volume of training data. Now, one single machine, because still our hardware is very constrained, we still cannot put all the training of these large models on one single machine. What we usually do is we collaborate. We take a lot of different computing units and we put them together and they communicate with each other. And that's how they are able to scale. They are able to scale with the rising data, the increasing model sizes. And this brings us to distributed, or recently popularized as federated learning. Now, what's happening in federated learning is that you're not storing the data at one machine anymore. The data is stored at different machines. These machines come together and they communicate and each machine, with the help of a server, they communicate so that you can minimize, you can attain the same objective as you would have done in the traditional centralized learning. So you want to minimize the average losses on these data clusters. So what's happening is you don't have one data cluster, you have several data clusters, and you're learning a model that minimizes the average loss that you have on these data clusters. And this is, in this one slide, I'm summarizing almost 99% of artificial intelligence for you. This is what's going on behind all these complex models, okay? You have a model, you start iterating this model over data, and you want to minimize your loss functions on the cluster of data that you have at hand, okay? The problem with conventional algorithms is that you have to trust all the data, and you have to trust all the machines. Now, why am I saying it now? Because this was an issue even before. Even before, you could have said, okay, I am collecting data at one server. I still have to trust my data and still have to trust this big machine that's learning. But now what's happening is you are trying to dissipate your learning. You're trying to use a cluster, a distributed network of clusters. And each cluster has its own data, and often you don't even get to see this data. Not just because of communication costs, but also because of laws of privacy. You cannot just ask these days a person to send all its images on the phone, on the server. It's you somehow compromise the privacy. So because of this, the data is getting distributed. And then it becomes more challenging to ensure the quality of such distributed data. The labeling of this data is done locally by the machines. And there are no mechanisms, there is no way to check whether these labels are correct unless you infringe the privacy of the user. Similar is the issue with machines. Because you have machines over the network, and often in thousands of these machines coming together, it's very difficult to keep a check on the computations done by these machines. The conventional techniques of error correction coding and redundancy are very expensive, and often industry, when they are learning these large language models, they are not implementing those schemes because, as David said, they are aiming for speed rather than safety. Okay, so why is this a problem? because a simple mechanism of just collecting the data and collecting the local updates and just averaging them can be compromised by a single machine. And on this, I'm going to show you some numbers that are just very surprising how fragile these standard machine learning algorithms are to these kind of very naive corruptions. And so the reasons for this behavior need not even be very malicious. You know, you can have. For example, some of the data may just get poisoned. Poisoning need not be intentional. When you are storing data, you can have some errors while registering the data. When you are labeling data, believe me or not, most of these labels are done by humans. These companies, they pay some volunteers, they give them some images, they ask them to label whether this is a cat or a dog. Many times, these humans, they just label randomly just to show that the work was done and they receive the payment. So, and another issue that we have, I think, which is very common in computer science, is you may have viruses. These machines may have viruses without even knowing they might be communicating erroneous information. You may have bugs in your hardware, you may have bugs in your software, and these are not any issues of modern times, but ever since computer systems have been developed. In extreme cases, you may have these bugs inserted by malicious players trying to manipulate the learning models or the training of your autonomous driving models and these kind of things. Just sometimes people do it just because, just out of fun, I guess. And then, for example, I'm going to show you a very simple case where you can have poisoning of data without even knowing, without even realizing. So this is one of the oldest machine learning data that students have been using in their classes. Every time a student learns how to model, how to train a machine, it tries to recognize handwritten digits. So the objective is you have handwritten digits and you have to tell by scanning them whether these digits is a 1, 2, 3, or 4, right? Now, it's fairly common that you are asking these digits are labeled by humans before you feed them to a machine. It has been often seen that a lot of people, the way they write 4 can be misinterpreted as 9. The way they write 9 can be misinterpreted as 4. Now, something I also learned in Switzerland is like a lot of people would think this is 1. And this creates a lot of issues. So you see, it's just a different way of labeling data that creates these issues. Another very common issue that we are seeing more frequently is because you are computing a lot of bits, it's very common for bits to toggle without you realizing them. And one of the grave consequences of bit toggling could be change of sign. When you're computing updates, you could change the sign of your updates, and then you are sending your model in a different direction than where you intended to. And a more complicated issue that we have these days is most of the data is being harnessed from internet. It is getting ever difficult to identify whether this data is coming from a chatbot or an actual human. Even I cannot tell it. A lot of conferences in machine learning are trying to identify if the reviews are written by chatbots, if the papers are written by chatbots. I can assure you that this is not a trivial problem, perhaps requires a whole conference of its own. And what we are seeing, these are again some old research, but the thing is these social bots, chatbots are rising by the day. I think people right now are claiming that in fact 70% of the people on Twitter are not real, okay? Without you, you often don't even realize you are retweeting tweets generated by some chatbots. And often this is a confusion, even for humans, whether this text is generated by an LLM or a human. So I can imagine a machine has no way of saying. So when a machine is using and harvesting all this data, often it is taking into account poisonous data, harmful data, corrupted data, data that manipulates these models towards some biased opinions. So the question, again, coming back to how do people in computer science, how do mathematicians, people who design algorithms should tackle this issue? So the question we are essentially asking here is, can I trust without Can I learn without trusting my sources? Okay, a parallel to this in real life is something as follows. In traditional times, even when I was in school, we would go to school, we would listen to our teachers, we would trust whatever knowledge they are giving to us. Things have changed a bit. Today, we are not just going to schools, we are also going on social media. We are going on YouTube, TikTok, a lot of things I don't even know. And we are trying to gather information from these. But is all of this information crap? Probably not. Some of this information is also true. And the task is now much more difficult because you have to identify what information to learn and what information to discard. And how do I formalize this problem? And one way we came up with is this topic of robust machine learning. And what we say is, okay, let's consider this underlying framework of learning a model. Now, what we are going to say is that F, let's say, of these clusters of data are adversarial. If you have N clusters of data, F of them are adversarial. And I don't know how they behave. They could completely behave in an erroneous manner, arbitrary way. We don't put any constraints on them. Okay? And I don't even know their identity. But I know that some of the clusters, some of the data is coming to me is corrupted. So we formalize our learning problem as saying, okay, we want to minimize, perform well on the data that is not corrupted. So we come up with an abstract optimization problem. We don't even know this optimization problem. It's an abstract notion saying we want to minimize only over the losses of uncorrupted data clusters. The problem is that we don't know this. And this is the challenge that we are trying to tackle right now, trying to learn from data sources using machines on networks where we don't even know which data sources to trust and which machines are behaving correctly. And this is the entire goal of robust machine learning. And this particular topic is, although it's emerging and it's the need of time, is not something very new. It's at the confluence of many different topics, areas in computer science that we already know. Of course, it is machine learning. It is what Turing dreamt of. We try to automate the programming. But it's also distributed computing, because we are trying to distribute the computing over different clusters, over different machines. And then it's also robust statistics, a field that many of you may not know, but was originated in Switzerland, where we try to estimate the true observations, the true parameters out of corrupted observations. And there are three inherent challenges that I'm not going to go into details, but are something that lay the foundation of robust machine learning. One is stochasticity. Even in machine learning, if you are aware, you have randomness. The way you sample data is random, not deterministic. This creates an issue. This creates challenges for existing methods in distributed computing. Similarly, you have heterogeneity. Clusters are coming from different populations. Often you don't know whether this cluster is corrupted or is just representing a different population. And of course, you have privacy. You cannot just ask these clusters to upload the actual data. You have to somehow preserve the privacy of the data while preserving the robustness. And these are some of the examples that I'm going to skip just because I'm running out of time. But these are some simple experiments that we have done using these methods. And even as a task as simple as identifying handwritten digits can be completely broken when you have these simple, very simple data poisoning in your system. And heterogeneity is creating much more challenges to us. And as you can see, almost the accuracy goes down to 20%, 30%. That's as good as just randomly classifying. And now, just to summarize my talk, because we believe that this topic is very important right now, it should be a part of any machine learning curriculum in any university or even industries. If someone is designing these models, he should or she should be aware of these threats, or how to tackle these threats, how to design these AI models, these machine learning algorithms that are safe towards corruption. So we, together with Rashid, who's the head of the distributed computing lab, And Rafael, we wrote this book which outlines all the progress that we have made in the last decade towards AI safety and robustness of machine learning. Thank you very much. With that, I would like to conclude.